This video is a step-by-step solution for the example entitled Analyzing Two Processes in Series. In this example, you will learn about analyzing two processes in series for superheated steam in a closed system, undergoing a compression followed by a cooling. In this example, you will also learn to compute the work and the heat transfer for each process. Let's look at the problem statement as given to us. Water contained in a piston cylinder assembly undergoes two processes in series from an initial state where the pressure is 10 bar and the temperature 400 degrees C. Process 1 to 2, the water is cooled as it is compressed at a constant pressure of 10 bar to a saturated vapor state. And process 2 to 3, the water is cooled at constant volume to 150 degrees C. Sketch both processes on the TV and PV diagrams. For the overall process, determine the work in kilojoules per kilogram. And for the overall process, determine the heat transfer, also in kilojoules per kilogram. First, let's do a critical read of the problem statement, highlighting in red the important information given and in green the information requested. Highlighted in red for the information provided, we have the following. Water, contained in a piston cylinder assembly, undergoes two processes in series from an initial state where the pressure is 10 bar and the temperature is 400 degrees C. Process 1 to 2, the water is cooled as it is compressed at constant pressure of 10 bar to a saturated vapor state. Process 2 to 3, the water is cooled at constant volume to 150 degrees C. Highlighted in green, for the requested information, we have the following. Sketch both processes on the TV and PV diagrams. For the overall process, determine the work in kilojoules per kilogram. And for the overall process, determine the heat transfer in kilojoules per kilogram. Let's start to develop the solution. The first thing to do in any problem solution is to summarize what is known. This is essentially the same information we highlighted in red in a critical read of the problem statement, presented here in a bullet list format. Water, contained in a piston cylinder assembly, undergoes two processes. It is cooled and compressed while keeping the pressure constant, and then it's cooled at constant volume. The next thing to do is to summarize what we have to find. This is again the same information we highlighted in green in our critical read of the problem statement, presented again as a bulleted list. Sketch both processes on the TV and PV diagrams and determine the net work and the net heat transfer for the overall process per unit mass contained within the piston cylinder assembly. The next step in the solution is to develop a relevant schematic. In this case, it was provided to us. However, let's highlight a few important pieces of information that were provided, which will help develop our solution. The first thing to note is there's no mass entering or leaving the piston cylinder. This immediately suggests that a closed system approach is the correct one. Having recognized this important fact, let's select our system boundary. In our case, it is selected to enclose the water in the cylinder and follow the physical boundary of the piston cylinder assembly as delineated on the schematic with a red dashed line. The next step is to develop an engineering model, which is a set of simplifying assumptions which will allow us to perform the analysis of the problem. The water is a closed system. The piston is the only work mode. There are no changes in kinetic or potential energy. The next step is to develop the appropriate thermodynamic diagrams to represent the processes as requested for Part A. The PV diagram and the TV diagram. Note that both diagrams show the vapor dome as the substance is water. Let's highlight both diagrams with the information provided at state 1. Since at state 1 the temperature T1 is equal to 400 degrees C is greater than the saturation temperature corresponding to P1 equal to 10 bar, which is 179.9 degrees C, state 1 is located in the superheat region to the right of the vapor dome. The process from 1 to 2 is a cooling at constant pressure, hence P1 is equal to P2, represented by an horizontal line on the PV diagram, and along an isobar on the TV diagram until we reach state 2 on the right edge of the vapor dome for saturated vapor state. Note that the specific volume and the temperature both decrease during the process. The process from 2 to 3 is a cooling at constant volume, hence V2 is equal to V3, represented by a vertical line on both the PV diagram and the TV diagram until we reach state 3 at a final temperature T3 is equal to 150 degrees C. Having completed all the preliminary steps for our solution and represented the processes in the PV diagram and TV diagrams as requested for Part A, let's develop the analysis. For Part B, since the piston is the only work mechanism, we can express the work for the whole process as W is equal to integral from 1 to 3 of PdV, which is equal to integral from 1 to 2 of PdV plus the integral from 2 to 3 of PdV. The second integral from 2 to 3 vanishes because the volume is constant in this process. During the first process from 1 to 2, the pressure is constant. Hence, after collecting the remaining term and dividing by the mass, we obtain the following expression for the work per unit mass: W over m is equal to P times V2 minus V1. The specific volume at state 1 is found from the table of properties of superheated water vapor at P1 equal to 10 bar and T1 equal 400 degrees C. This gives us a value of V1 is equal to 0.3066 cubic meters per kilogram. Similarly, we can find the value of the internal energy. U1 is equal to 2957.3 kilojoules per kilogram. Finally, the specific volume at state 2 is the saturated vapor value at 10 bar, V2 equal to 0.1944 cubic meters per kilogram, obtained from the pressure table of the properties of saturated water. Substituting the numerical values for the properties and paying attention to unit conversion, we obtain the value for the work per unit mass for the entire process as follows. W over m is equal to minus 112.2 kilojoules per kilogram. Note the conversion from bars to pascals and joules to kilojoules to calculate the work per unit mass in kilojoules per kilogram. This is the answer to Part B that we were seeking, namely the work per unit mass for the entire process. The minus sign indicates that work is done on the water vapor by the piston. For Part C, an energy balance for the overall process reduces to m times U3 minus U1 is equal to Q minus W. After rearranging the terms and dividing by the mass, we get an expression for the overall heat transfer. Q over m is equal to U3 minus U1 plus W over m. To evaluate the heat transfer in the expression we develop requires U3, the specific internal energy at state 3. Since T3 is given and V3 is equal to V2, two independent intensive properties are known to have fully defined state 3. Recall from the TV and PV diagram that state 3 was inside the vapor dome. So we need to determine the mixture quality in order to evaluate the internal energy U3. From the definition of the quality, we get that X3 is equal to V3 minus VF3 divided by VG3 minus VF3. After substituting the numerical values for Vs3 and Vg3 from the temperature table of properties of saturated water at 150 degrees C, we obtain the following, giving us a value X3 is equal to 0.494, which is clearly inside the vapor dome. Using the quality X3 we just calculated allows us to evaluate the internal energy at state 3. U3 is equal to UF3 plus X3 times UG3 minus UF3. The values of UF3 and UG3s are given again from the temperature table of properties of saturated water at 150 degrees C. After numerically evaluating the expression, we get a value of U3 is equal to 1584 kilojoules per kilogram. Substituting into the energy balance the numerical value for the internal energies at state 1 and 3 and the work per unit mass for the process, we get the following, giving us a value Q over M is equal to minus 1485.5 kilojoules per kilogram for the heat transfer through the overall process. This is the answer we were seeking for part C. The minus sign shows that energy is transferred out by heat transfer, corresponding to a net cooling. Quick quiz. If the two specified processes were followed by a process 3 to 4, during which the water expands at a constant temperature of 150 degrees C to a saturated vapor, determine the work in kilojoules per kilogram for the overall process from 1 to 4. You may want to pause the video at this point to work out the solution. The answer is W over M is equal to minus 17.8 kilojoules per kilogram. Hopefully, this matches what you have obtained, and congratulations. If not, you may want to review the various steps in the video and recalculate the answer. If you still do not get the correct answer, here are a few hints on what you need to do. At state 3, is within the vapor dome, at X3 is equal to 0.494 as computed earlier, the process from 3 to 4 is at constant temperature, is also a constant pressure process corresponding to the evaporation of the water until saturated vapor state at state 4. Hence, the work is given by W3 over M is P3 times V4 minus V3. Evaluating V4 is equal to Vg4 from the temperature table of properties of saturated water at 150 degrees C is left as an exercise. The total work from 1 to 4 is the sum of W13 over M evaluated earlier and W34 over M evaluated just now. In closing, in this example, we have learned about analyzing two processes in series for steam in a closed system. We have also learned how to compute the work and heat transfer for each process. This example is an important building block for analyzing thermodynamic cycle made of several processes in series, typically 4 or more. The methodology will remain similar, evaluating relevant thermodynamic properties at each state, enabling us to evaluate energy changes by heat or work from one state to the other. This concludes the step-by-step solution of the example entitled Analyzing Two Processes in Series.